Hi guys, it's Miss Crystal here, and going back with our theme of Germany, I have a STEM activity for us today. So the kind of central theme for today's activity revolves around Albert Einstein. He's a very famous German scientist. You guys have probably heard of him. He's right up there with Isaac Newton, and I guess those two are the most famous scientists. Well, either way, today's activity is dealing with the speed of light. So, you guys have probably seen Albert Einstein's famous equation of E equals mc squared. This equation is famous because it helped us figure out the speed of light. The equation we're going to be using today is way simpler than this, but just so you know, this was Albert Einstein's equation that helped us discover the speed of light. Alright, so before we begin, we need to have a quick discussion about light and wavelengths. So, light actually moves in wavelengths, just like this. Different frequencies move at different wavelengths, but they're all considered wavelength. Just like microwave wavelengths is just a different frequency that the light moves at along this wavelength pattern. So the way that microwaves work is as it powers on and you have it turned on and it's heating up your food, the wavelengths inside the microwave actually move up and down like this. This is a static image, but it actually goes kind of up and down. And it'll move constantly throughout the microwave. And that's how it heats up the food, is this wavelength is traveling through your food to heat it up. And the reason why it has a rotating tray is this wavelength has certain ups and downs that it goes through. And so when it goes through that, that means it's only technically heating up certain spots in your food. And we rotate it, that way it distributes the heat more evenly. So, going over what we need, this activity is actually pretty simple. All you need is a microwave-safe dish, which is why I'm using my paper plate. Something to microwave that melts. I'm going to be using chocolate, but you could use like marshmallows or maybe even butter if you can. Just anything as long as it melts. And a ruler, one that has centimeters on it, because we need to measure our thing in centimeters. And the last thing we need for this experiment is we just need a regular old microwave. Any old microwave will do. However, the only thing we need to do to our microwave is if yours has this rotating tray on it, like most do. Mine's a little bit dirty, sorry about that. We just need to take it out for this experiment. And as you can see, I've gone ahead and I've removed the rotating tray from my microwave. The reason why we took this out, because if you go back to our wavelength diagram, you'll remember that the wavelength moves up and down as it moves. So that's how it heats it up. And the rotating part is, again, just to keep it moving so it's not just the same spots getting heated. But that's what we need for this activity. We just need like certain spots to be heated. It'll make more sense when you see what I'm talking about, trust me. So we also need to know the megahertz or the hertz or the frequency at which the microwave heats food. Most microwaves have a wavelength of about 2,450 megahertz, or what's that? 2,450 million hertz. This is what my microwave has. You can find it on your microwave, usually along the back side. I checked mine, and this is what mine was, and this is what they are for most microwaves. So the next thing to do in our activity is just to microwave our chocolate or our marshmallows or whatever we're using that melts in the microwave on low for a few seconds. It's hard to tell exactly how much time it takes. Usually about 20 to 25 seconds I found is good. You're just gonna have to kind of play with it yourself. And again, we don't want the chocolate completely melted. It's just gonna look just until it starts to melt, which I'll show you what it looks like here in a minute. All right, and here is my chocolate once it's done doing the beginning to melt in two places. Now, what I did was right after I saw that it had started to form what we wanted to, here, let me get a closer look. Just like that, I just took it out and I stuck it in the fridge for a few seconds just to let it harden back up again a little bit. That way we wouldn't hurt ourselves or mess up the experiment when we go to measure it. Because trust me, hot chocolate burns. Alright, so now again, the next step is to measure the distance between these two melting points, where it kind of began to bubble and melt. It's a little bit harder to see on the camera, but maybe that's a closer look. So what we're going to do is we're going to take our ruler. It has to be on the centimeter side. In the science community, they use centimeters rather than inches, which is why we had to make sure our ruler had centimeters. And we're just going to measure the distance between our two melting points. Now, I've kind of already gone and done this off camera just so I knew where to measure, because it is a little bit hard to do with one hand. But going from one edge to the other, it looks like it's about 5.5 centimeters. So if you have a bigger piece of chocolate, you'll be able to get more bubbling points throughout your chocolate. And if you measure the distance between each one, they should all be roughly the same. That's how you know you've done it right. Unfortunately, my piece of chocolate is a little bit smaller, so I wasn't able to get more than 2. So now to get into the math part of our experiment. I know it's the most interesting part, sarcasm. So we measured our wavelength in the microwave and we got roughly 5.5 centimeters. Now, what we have here, that's actually half the wavelength. The microwave doesn't have the full wavelength. We only got half. So what we have to do is we have to times this by 2 in order to get 11 centimeters. And then we just, again, as a reminder, our microwave is 2,450 megahertz or 2,450,000,000 hertz. That is the roughly the frequency of our microwave for the wavelength. So what we're going to do is we're going to times our frequency by the wavelength, which is going to, spoiler, we're going to multiply the hertz of the microwave times the length of our wave. The frequency of our microwave times our wavelength. And that's going to be a big number, so let's go ahead and do it in the calculator. And that's the number we got, 26,950,000,000. I think I said that right. So now we're going to compare this to the actual speed of light. Drum roll. That's kind of a sad drum roll. And 29,400,000,000. So as you can see, our numbers were kind of close. So I tried this experiment a few times before filming it, and I got different distance between my bubbles when I was microwave. Sometimes I got 6, sometimes I got 5. This time I got 5.5. So it's kind of in between. It really all depends on your microwave. Mine's kind of old, so it's not consistent. And it kind of took a little bit to microwave. So as you try it, you should always be kind of close if you do it a few times. My numbers were pretty close. So I bet you if I were to try again, maybe with a bigger piece of chocolate or on a newer microwave, I might get something a little bit closer. But I just wanted to show this as to kind of show that sometimes, you know, you don't always get the exact answer when it comes to doing experiments, but as long as you get something close, you know you've done it right. Anyways, I hope you had a lot of fun and hopefully learned something. I'll see you again soon. Bye!